In this presentation, we'll talk more about using the inverse Laplace transform and how to make a frequency domain signal ready for taking the inverse Laplace transform. And as we noted in our last presentation, we won't need to do the actual integration in the complex plane. We can use Laplace transform tables for this purpose instead. And when we use Laplace transform tables, we'll be using ones for the unilateral Laplace transform, which you find in your book. One of the important items that we will discuss in this presentation is partial fraction expansion. This is a key step in preparing a signal in the frequency domain for the inverse Laplace transform that we find in our tables. Before going any further, we'll need to discuss the linearity property of the Laplace transform and the inverse Laplace transform. In a future presentation, we'll actually discuss many properties of these transforms, and these will be important to analysis. But for now, let's restrict ourselves just to linearity. What do we mean when we say the Laplace transform, or the inverse Laplace transform, is a linear operator? Consider two signals, x1 of t and x2 of t. Laplace transform of x1 of t is x1 of s, and Laplace transform of x2 of t is x2 of s. All we're doing here is defining what we mean by x1 of t, x1 of s, x2 of t, and x2 of s. Let k1 and k2 be some constants. The linearity property then says Laplace transform of the quantity k1 x1 of t plus k2 x2 of t is equal to k1 times x1 of s plus k2 times x2 of s. This same linearity property holds for the inverse Laplace transform. Now the linearity property of Laplace transform and the inverse Laplace transform is actually very easy to prove. All you have to do is go back to the definition of what the Laplace transform means, that definition being the integral. And you can easily see that the property that we've discussed here holds. Let's do an example of taking the inverse Laplace transform where we employ partial fraction expansion and then the linearity property of the inverse Laplace transform. So we'll start with x of s is 10 over s squared plus 11s plus 10, which we can write as 10 over the quantity s plus 1 times the quantity s plus 10. We can take that and partial fraction expand it, and we'll discuss partial fraction expansion in greater detail later in this presentation. After partial fraction expansion, we'll have the quantity 10/9 over s plus 1 minus 10/9 over s plus 10. And if you multiply it back out, putting it under a common denominator, you'll find this is 10 over the quantity s plus 1 times the quantity s plus 10. So now that we've written x of s as two simple terms, we're ready to do the inverse Laplace transform. So x of t is the inverse Laplace transform of x of s, which is the inverse Laplace transform of 10/9 over s plus 1, plus the inverse Laplace transform of negative 10/9 over s plus 10. You see here how we're using the linearity property of the inverse Laplace transform. Then carrying out the last step, we find that the inverse Laplace transform of x of s, which is x of t, is 10/9 times e to the minus t minus e to the minus 10t u of t. We'll now introduce two important terms, and we'll use these terms throughout the rest of the class. You should be sure to understand what each of them means. The values of s such that x of s is equal to 0 are called the zeros of x of s. The values of s such that x of s goes to infinity are called the poles of x of s. For example, if x of s is s minus 3 over s plus 1, this x of s has a 0 at 3, since if we plug in s equals 3, we have s minus 3 equal to 0. And this signal has a pole at minus 1, because s plus 1 will go to 0 at minus 1, and therefore x of s will go to infinity. Let's suppose that h of s is the ratio of two polynomials, p of s and q of s. We write h of s is p of s over q of s. Then the roots of p of s are the zeros of h of s, and the roots of q of s are the poles of h of s. Now, if a function cannot be written as the ratio of polynomials, it still may have poles and zeros. They just won't be as easy to find as taking the roots of a polynomial. In the example earlier, I mentioned partial fraction expansion as an important step when we're turning signals from the frequency domain to the time domain. I'd like you to know how to perform partial fraction expansion when the poles are distinct. You should learn also how to perform this task in MATLAB. The details of partial fraction expansion are covered in many textbooks. In this presentation, I'll go through partial fraction expansion for a simple example. I'll do this mainly as a reminder to you about the technique. You should consult your textbook for more details about partial fraction expansion. We'll do partial fraction expansion of a signal with distinct poles. Our signal for this example is x of s equals 7s minus 6 over s squared minus s minus 6. Our first step in the partial fraction expansion is to find the poles of the signal. For that, we take the denominator polynomial and we find its roots. So the roots of s squared minus s minus 6 are minus 2 and 3. In step 2, we factor the denominator polynomial. So we write x of s is 7s minus 6 over s minus negative 2 times s minus 3. You note that we have taken the denominator and written it in terms of the poles. Each factor is s minus one of the poles. Simplifying this, we get 7s minus 6 over s plus 2 times s minus 3. Our third step is to write the signal as expanded. So x of s is equal to k1 over s minus minus 2 plus k2 over s minus 3. Our fourth step in the partial fraction expansion is to find the constants k1 and k2 by the cover-up method. In this, we cover up one of the factors in the denominator and then let the value of s go to the root of that factor. So k1 is 7s minus 6 over s minus 3 when we set s equal to minus 2. The s minus minus 2 term has been covered up. It's not there. And we set s to be the root of that expression. Substituting in s equals minus 2, we find k1 is equal to 4. In exactly the same fashion, we find k2, except this time we cover up the factor s minus 3, and we let s equal to 3 in the remainder. We find k2 equals 3. In step 5, we plug in the k values just found back into the expression for x of s, and we find x of s is 4 over s plus 2 plus 3 over s minus 3. We've now accomplished the partial fraction expansion. With the partial fraction expansion completed, in step 6 we perform the inverse Laplace transform, and we use the table for this purpose. So x of t is the inverse Laplace transform of x of s, which is the inverse Laplace transform of 4 over s plus 2 plus 3 over s minus 3. We can then write that as 4 inverse Laplace transform of 1 over s plus 2 plus 3 inverse Laplace transform of 1 over s minus 3. Here we're using the linearity property of the inverse Laplace transform. We then can consult the table and find that the inverse Laplace transform of 1 over s plus 2 is e to the minus 2t, and the inverse Laplace transform of 1 over s minus 3 is e to the 3t. Therefore, x of t is 4 times e to the minus 2t plus 3 times e to the 3t. Now, we must remember that we're using the unilateral Laplace transform, so every signal we deal with must be causal. To write the solution correctly, we should note this. So x of t is the quantity 4e to the minus 2t plus 3e to the 3t, all multiplied by u of t. So the main steps in getting from the frequency domain back to the time domain are partial fraction expansion and then the use of the Laplace transform table. In a moment, we'll examine how to use MATLAB to do the partial fraction expansion. But first, this musical interlude.
Use the table. Your Margarian table. Page 344. What do you see?
Table 4.1, table 4.1, table 4.1, table 4.1, table 4.1, table 4.1, table 4.1.
I fear for our nation. We'll now review how to use MATLAB to do the partial fraction expansion. We'll do the same example as previously. X of s is 7s minus 6 over s squared minus s minus 6. The double arrows indicate the lines that you type in at the prompt. In MATLAB, a polynomial is represented by an array of its coefficients. So the numerator of x of s, 7s minus 6, is represented in MATLAB as the array 7 minus 6. Our first line here, num equals 7 minus 6, defines the numerator polynomial. Our second line does this for the denominator. The denominator is s squared minus s minus 6. The coefficients are 1, minus 1, and minus 6 for this polynomial. So our second line defines the denominator polynomial. We then use the residue command to do the partial fraction expansion. We write rpk equals residue num den. The num den arguments give the numerator and denominator polynomials to the residue command. The residue command then returns r, p, and k variables. The variable r is an array of the residues. These are the coefficients k1 and k2 that we encountered before that appear in the numerator of the expression after partial fraction expansion. P is an array of the poles. As we found before, they are 3 and minus 2. The variable k is a constant, resulting from the partial fraction expansion if the order of the numerator was the same as the order of the denominator. When you type in rpk equals residue numden at the command line in MATLAB, it will return these variables. So MATLAB has now performed the partial fraction expansion, but we need to interpret its output. It returned the variables r is the array 3, 4, p is the array 3 minus 2, and k is the empty set. What this means is that the residues of x of s after partial fraction expansion are 3 and 4. The poles are 3 and minus 2, and that there is no constant term that needs to be included in the partial fraction expansion. Note the order. The order of r is 3 and 4. The order of p is 3 and minus 2. This means the first residue, r equals 3, is associated with the pole 3, and the second residue, r equals 4, is associated with the pole at minus 2. So we write the partial fraction expansion as x of s is 3 over s minus 3 plus 4 over s minus minus 2 plus 0, since there is no constant term, as indicated by k equals empty set. Let's now look at one more example of using MATLAB to do the partial fraction expansion. And in this example, we'll have repeated poles. So, our example is x of s is equal to 2s squared plus 7s plus 4 over s cubed plus 5s squared plus 8s plus 4. So our numerator polynomial is defined by the coefficients 2, 7, and 4. And our denominator polynomial is defined by the coefficients 1, 5, 8, and 4. So we define those in MATLAB with the num equals 274 command and the den equals 1584 command. We then use the residue command. with the arguments numden as before, and find r, p, and k. MATLAB returns r is 3, 2, minus 1. P is equal to minus 2, minus 2, minus 1. And k is empty set. So now the question is how to interpret these results. Again, ordering is very important to properly interpreting the results that MATLAB returns. Our residues are 3, 2, and minus 1. Our poles are minus 2, and minus 1. The order is the same here. The residue 3 is associated with a pole of minus 2. The residue 2 is associated also with a pole of minus 2. And the residue minus 1 is associated with a pole at minus 1. In the case of repeated poles, the first residue associated with the repeated pole is the one given for the lowest power of that factor in the partial fraction expansion, the lowest power being the first order power of that factor. So the residue 3 associated with the repeated pole at minus 2 appears in the partial fraction as 3 over s minus minus 2. The second residue given for this pole, 2, then appears in the numerator of the term 2 over s minus minus 2 squared. Since it's the second residue given, it appears over the factor squared. If a pole was repeated 3 times, and we had 3 residues, the third term would be over s minus the pole cubed. So our partial fraction expansion, properly interpreted from MATLAB, is x of s is 3 over s minus minus 2 plus 2 over s minus minus 2 squared plus negative 1 over s minus negative 1 plus 0, since the constant term is given as 0 because k is the empty set.